Okay, welcome to the next installment of the podcast, and this is going to be the first physics podcast that we do. And this physics podcast is going to be all about forces. Okay, in terms of marks, these can range from a couple of marks from different diagrams, but the basic understanding feeds into so many marks. So this is the crucial part here. So we're going to do it as always, diagrammatically. And the first thing to understand is all about this thing called resultant forces. Now, resultant forces just quite simply means taking all forces into consideration, what is the result going to be? So, let's have a situation where we've got a ball travelling in this direction here. This direction. So here's my little comedic cartoon marks. So this ball is moving this way. So, while it's moving, let's now add some forces and describe the state of motion it will be in. So, the ball, if we apply a big force this way, and a smaller force opposing that, from now on, this ball is going to accelerate. It's unbalanced in its forces. It's going to accelerate. It's going to get faster and faster and faster. That is state of motion number one, acceleration. Well, let's say we had a big force opposing its motion. The smaller force over here. And again, that will be unbalanced. And that ball will slow down. It will decelerate. Decelerate. Okay, next. And this is a tricky one. So let's say this ball's moving, and we apply a force like this, and then we apply the same force in the opposite direction. So these two are meant to be the same size arrows. In that case, it's not going to get faster, is it? It's not going to get slower. As we can see here, this one had to be bigger than this to make it faster. This one had to be bigger than this to make it slower. These two are the same size. So it's going to be balanced. And it's going to be at a constant velocity. So the speedo is going to stay at 20 miles an hour or 10 miles an hour, 10 meters per second, whatever that is at that time. Now the last one, let's say we got the ball, it was stationary. And then we applied equal and opposite forces. Then it would remain stationary. Balanced. Stationary. And they are your four. 1, 2, 3, 4. 4 states of motion something can be in. And the resultant is quite simply, well, okay then, what's the resultant force for this one? Well, we've got a big force there, a little force there, so overall we're going to have a medium force going this way. So it's that minus that, effectively. The result for this one, small force, big force, medium, this way. And so on. So that is the basic principle to this podcast. These ideas. And like I say, they feed into so many principles throughout the questions. So let's go down here and have a look at some distance, time, velocity, time graphs. So we can describe a journey using a graph. If we have time along here, and time is in seconds, and we have distance as in meters, then we can describe someone's journey. So let's say a car. It can do these things here. So what is the car doing at each point? You put some numbers up here, it will make it simpler. So, first 20 seconds, the car is gone from 0 meters to 30 meters in 20 seconds. So it is moving. So it has a constant velocity here. Here though, have a look at these next 20 seconds from 20 to 40. The distance has remained at 30 meters. You haven't gone anywhere. You stayed at 30 meters for 20 seconds. Like staying at some traffic lights. So here, this is stationary. No distance has been moved. It's stopped still. Time has gone by, tick tock, and they've gone nowhere. Now, Again, they're moving here, but let's compare this line to this line. It's a shallower line, so this is a slower constant speed, constant velocity. So if you compare this to this, this is 40 meters per second, and that's 20 meters per second. So it's still got a constant velocity, but a slower rate. Now the next graph, probably the most frequent graph you'll come across, is a velocity time graph. Time along the bottom again. Am I in shot? No, let's move it up. Time along the bottom again. Velocity up the side, meters per second. And we've got different shapes you need to recognise. So, let's put some numbers in. Right, so let's have a look at this then. So this one, its speed, its velocity, has gone from 0 to 30. So what is it doing there? It is accelerating, it's getting faster. It started off in a stationary position and got up to 30 meters per second, so it's accelerating. Someone's put the foot on the accelerator. Here, look, 30 meters per second. So this is a constant velocity. It's not stopped, it's got a velocity, but it's just staying at 30 meters per second all that time. At this point, after 50 seconds, they put the foot on the brake, and the speedo, if you had one in the car, it just dropped down. So going from 30 to 0. That is decelerating. Okay? Right. Let's move over. Last thing for this podcast, and that's going to be around terminal velocity. Understanding terminal velocity and how we show that on a graph. And this is where my bad diagrams come in, but I make no excuses because I enjoy myself when I do them. So, terminal velocity. Underlined. Right. This is the side of my plane. And that's my person sitting in the plane. And then each stage I'm going to comment on what force is acting on him. So, he's sat on the plane, he's not moving anywhere. The plane's moving, of course, but he is not moving anywhere, or she's not moving anywhere. So, at this moment in time, you've got a upward force and a downward force that are equal to each other. They are balanced. Going over to here, balance, it can be either one or two things, and they aren't moving anywhere, so it's stationary. Stationary. Right, they make the leap of faith out, they go, ah, and they jump out. I'm just going to do it like that. That's his head, that's his feet. Okay? Not wasting time on drawing diagrams. So gravity, combined with mass, is going to contribute to the person's weight, and they are going to fall. And at this point, the air resistance opposing the movement, so air resistance, weight, is air resistance is going to be less, so they're getting faster. They're going from nothing to something, and they are therefore accelerating. And they're going to continue to accelerate. This weight is not going to change. The person's mass doesn't change, gravity doesn't change on Earth. But as they get faster and faster and faster and faster, air resistance gets larger and larger and larger and larger. This point we're still unbalanced, so we're still accelerating. But at some point they're going to free fall. If they stay in the same position, this air resistance is going to get bigger and bigger and bigger as they get faster and faster until they equal each other out. They become balanced. And when they become balanced, the person has reached terminal velocity. The terminal velocity here. Balanced forces is a constant velocity. And for human beings, it's about 127 miles per hour in that stage. So, if they did this all the way to the ground, they would smash into the ground and kill themselves. So what they do is, they open up their parachute. Ding! So, Open up the parachute. And as soon as they open up the parachute, they're going to get a massive boom. Massive resistance force here. So they are going to decelerate. Unbalanced forces can either be acceleration or deceleration. They're getting slower. You know that. As soon as somebody opens the parachute, they slow down. But again, they will reach another terminal velocity that is a lot slower when the forces equal each other out. Terminal velocity for the second time. Constant speed. And that is the route of a skydiver. Now this can be plotted on a graph. So let's have a quick look at the graph. So this one here, accelerating, they are getting faster. So if I've got velocity, if I've got time, they are getting faster at that point. Velocity, 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 velocity. This one is still accelerating, getting faster, 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 faster. But at this point here, they reach terminal velocity. So they are going across here like this. So their velocity is not getting any more. It's staying constant. Until, of course, they open their parachute. At this point, they open the parachute, bang! Velocity comes all the way down. Slows down, slows down. But again, it reaches a terminal velocity, steady speed, until they hit the floor, and it goes dump, down to zero, stationary. And this is a graph showing somebody taking this route out of an aircraft. Do not forget, people, this happens in air and liquids as well. So if I dropped a ball bearing into a tube of water or into the sea, it would reach terminal velocity. Same principles apply. If we're talking about these forces being unbalanced, accelerating, balanced, constant velocity, terminal velocity, that is where you're going to pick your marks up if you get a 6 mark on there. Okay, have a go at the exam questions now. Thank you.